Okay, fine. So I will hold this presentation in English. Hope it's okay for everyone. You're very welcome to put questions in Swedish afterwards. So my name is Ola Kalén. I'm at this Swedish Met Office in Gothenburg, working with sea level rise, data analysis, and among other things. So I will try to go through the very vast subject of sea level rise. And it will mostly be a global outlook with a focus on polar ice sheets, because that's my research specialty also. If we have some time, I will take a short peek at what's happening in Sweden also. So I will I will do a short introduction with some theory and measurements, and then move on to how has the sea level risen in the past and what's happening now, and to end with some future projections. So we are now very sure that sea level is actually rising, and that's thanks to all the measurements we have. And from the 1800s and onwards, there has been measurements from tide staff. So that's basically a floating thing in the surface of the ocean that's connected to a pen that registers sea level rise in this way. And in Sweden, we have actually the oldest ongoing measurement series in Stockholm since 1774. And in modern times, we measure sea level with the radar. So all the news stations have double radar sensors. And these days we get data every minute. And there's about 60 stations or so in Sweden that are administered by the Swedish Met Office. And since the 90s, we can also measure the surface of the ocean from satellites. So with the start of the modern altimetry era, we can cover the whole globe and get very good updates on this on these measurements also. And apart from this, there's older proxy data. We can go back in geological time and with the help of coral sediments and also ice cores to judge how the level has varied in the way past. And what controls the global changes in sea level? So it's first here the internal change, that's thermal expansion, which happens when the sea gets heated up by the atmosphere. So when this happens, the water takes more place, and the volume increases, and that's I think that's been happening since the anthropogenic climate change and the heating of the atmosphere. So that's the internal change. And apart from this, the four other factors are external changes, and that's we change the mass of the ocean. So we input water into the ocean, and that comes from mountain glaciers, and also the two big ice sheets that we have, the Greenland ice sheet and the Antarctic ice sheet. And the last one here is land water storage. That's mostly big dams from hydropower and also groundwater use. And that has also a large effect. And then that's influencing things also is the vertical land motion, which is important in Sweden. We have a land rise. And there's also land subsidence, where the land is going downwards. And this can happen in, for example, the big mega cities that actually weigh down the crust of the earth. So these factors all together make up the sea level budget. But here's a saying that all sea level is local. What's important for society is what's happening at the coastline. And here there's more short-term effects also happening due to weather and tides and also the topography of the ocean here. So this is shorter time variability, which makes it harder actually to analyze sea level rise questions just at the coast. And what has caused sea level rise since the 1900s? This was actually for the first time last year. This was the first correct backwards budget for the sea level rise. And the summary from this paper is that it was the mass loss from glaciers that has caused the most sea level rise since 1900s, about twice as much as the thermal expansion from the heating. And in descending orders, it was the mountain glaciers, the Greenland ice sheet, and then the Antarctic ice sheet that was responsible for this sea level rise. And the average for this time is about 1.5 millimeters per year. But there has been an acceleration in this rise since the 70s due to increased thermal expansion and loss from the Greenland ice sheet. So now we're about 5 millimeters per year of sea level rise. And the dominant cause of this is the anthropogenic heating, the human climate change, the warming, which is very clear since at least the 1970s, according to IPCC SROC, which is the latest special report on the ocean and the cryosphere from the IPCC. I will bring this SROC up a number of times onwards here. So, and it's important also to look where is the potential sea level rise. That is, where is ice stored on land, which can be melted and input to the ocean in the future. And here are the big three terms. So to the far left are the mountain glaciers, and that's glaciers outside of the polar areas, for example, the Alps and the Andes, Himalayas. And they could melt, if all that ice melted, the global sea level rise would get about 0.5 meters higher or so. So this is the term that has had the biggest influence so far, but in the future, all this ice will be depleted more or less if we follow the high emission scenario in the long-term future. And if we look at the Greenland ice sheet, there's about 7 meters equivalent of sea level rise stored on the ice sheet. And most of this ice, very importantly, is on the inland. So I don't know if you're able to see my pointer. Yeah, so the ice is mostly stored inland here. Some parts are close to the ocean, and this is very important because if the ice also has connection to the ocean, it can be melted both from the heat of the ocean and the atmosphere. And to the right, Antarctica. So this has a sea level rise potential of 58 meters. And this is the big reasons why we are so interested in what's happening in Antarctica. So this is a huge potential of sea level rise. And this picture here also shows the ice bottom elevation. So this ice sheet here is thousands of meters thick. And in some parts, the bottom of the ice rests on bedrock that's way below sea surface. So this blue area here means that this is a couple of thousand meters below sea level. So the ocean can access the ice directly here. And this part to the left of this line is the West Antarctic ice sheet. That's the WISE. And this has sea level rise equivalent of about 4 or 5 meters. And you usually do this division here because the dynamics are quite different from these two parts here. Now we'll get into this a bit more later. So So usually when we talk about future sea level rise, it's the West Antarctic ice sheet that has all the fluff and gets all the attention. And this is why this is because things are happening really, really fast there. So Greenland down here gets, it's a bit sad that it doesn't get talked about as much, but Greenland is actually contributing to twice as much sea level rise as Antarctica right now. But as you saw before, the future potential for large sea level rise actually rests in Antarctica. And there was actually this new study from Monday, a very recent one, finds that the global ice loss is accelerating now very fast. And to the right, you can see this graph. It takes up all the different ice that's melting on the globe. So it's the floating ice. That's the Arctic and Antarctic sea ice, and also the grounded ice in Antarctica, Greenland, and glaciers. So the ice that's floating in the Arctic and Antarctic, that doesn't affect sea level so much. It's a small effect, about 5%. Usually you say that the floating ice doesn't affect the sea level rise at all, but that's not really correct. It's a small effect due to the freshening of the seawater. But the important thing for the sea level rise here is, of course, the grounded ice. So 28 trillion ton ice has melted during this period. It's a hard to fathom figure, actually. And also there's been an acceleration in this ice loss, and it has led to about 3 or 4 centimeters of sea level rise during this time. And all this ice was melted only due to 3% of the heat from the human climate change. So that's a surprising number, actually, that you don't need more heat to melt all this ice. And here is I tried to visualize how much is this ice really. So this is the ice that's melted every year, both the sea ice and from the ice sheet. So that's 1.2 trillion tons. So that makes an ice cube with about 10 kilometers per side, so covering more or less the whole of Stockholm here. So that's a pretty astonishing amount of ice that's melting right now. And here I will try to explain why, again, we're so interested in West Antarctica. So we can see that there's some differences around the whole perimeter, but the most important parts here that are melting really fast and losing mass, they're on the west side here. And that coincides with this one that shows the bottom temperature. So the warmest bottom waters are actually here on the west. And this sector here is open to the Pacific, and the influence here from what's happening in the central Pacific, it's very important with El Nino and also the warming of the Pacific that has a big influence on this western side here. And there are actually areas here that have a lot colder bottom temperature, and here the ice is growing. So it's big difference around the perimeter, but important areas on the west, but also some parts of the east are also melting. Important here is the Totten Glacier, where this warm bottom water has also been found. And among the west, the two important glaciers are the Thwaites and Pine Island glaciers. And there's now the biggest polar research effort ever conducted at the Thwaites Glacier. So there's lots of effort to find out what is happening there. And that's because these two glaciers only together have a potential of 1 meter of sea level rise. And very, very fast changes happening. So we need to actually find out what is happening. And the 1 meter will lead to even more sea level rise, because in the long term, these two outlet glaciers are connected to most of the West Antarctic ice sheet. So if we lose a lot of mass here, the rest of it will follow in a longer time scale. And now it gets a bit technical, but I will try to explain this process here, because this process is called marine ice sheet instability. That's the one process that holds the most uncertainty for the future sea level rise on the globe. So the ice sheet flows downwards towards the sea because of gravity. Remember, this is thousands of meters thick. So it will flow to the ice, and where it meets the ocean, it's called an ice shelf. This area here acts as a buffer to the ice sheet. And if you have a big, thick ice sheet, this speed will not be so high. But on parts of the West Antarctic side, the warm deep water has access to the ice shelf from below. So the ice gets melted from the underside. And the potential heat in the ocean is many, many times larger than the atmospheric heat in these areas. And important here also is the grounding line. This is where the ice is grounded in the bedrock, and here it leaves the bedrock and gets to be the floating point. So if this melting continues, the ice shelf will be thinner here. We will break off, we will carve off more icebergs here, and this force here, the buffering force, will get less, and this will make the ice sheet speed up here. And that in turn makes this grounding line go backwards. And the speed with the flow here gets faster if the grounding line here is thicker. So for this to happen, we need a bedrock that's sloping inwards at this point. So this is like a self aggregating, not aggregating, what you call it, a process that a positive feedback loop, I should say. So it gets faster and faster, this rise. And this kind of instability has been observed here and also reproduced in models. And it's very hard to reverse this process on longer time scale. You basically need to have a new ice age or something in the bedrock that kind of slows down this ice sheet. And both Thwaites and Pine Island are very much set up, the topography here, for this kind of instability. And now for some future projections. So, and first I would like to say that we're in for sea level rise for a very, very long time. This is nothing that we can reverse or take back in some way. A bit different from the atmospheric warming. So here is a model output that shows the sea level change in meters per 100 years over the very long time scale. So this is 20,000 years back. And this goes to the nowadays and then thousands of years forward. So these 4 lines are different warming scenarios. So this lower line is a lower warming scenario, and this is a high warming scenario. And what you can see from this picture is, regardless of the scenario, we will have sea level rise for a couple of thousand of years. But it's also a huge difference between the high emission scenario here that could give potentially 3, 4, 5 meters per 100 years of sea level rise. So this is basically built in now due to human warming, and that's the slow response of the ocean this heat needs to be spread out throughout the whole ocean, and this takes a long time. So we will have to deal with this in the future. And so for the more near term, here is the projections from the IPCC SROC. And here in the reddish field is the high emission scenario RSP 8.5. That is if the emissions will increase a lot. And there's the blue scenario, which means if we manage to stop emissions very quickly. And you can see there's a big difference going forward in time here between these two scenarios. So it's very important to try all we can to lower the emissions. It would mean a huge difference in the future sea level rise. So for the 2100, which has been a year that these projections usually have been going to, it says that it's 1.1 meter, and that's for the RSP 8.5, the high emission scenario. And that's the upper likely range. So that's judged to have a 17 to 83% probability by the IPCC. So we still run a 17% probability to get above this level. And it's also stated that we cannot rule out levels above 2 meters at 2100. And also another thing, for now I've been talking mostly about the mean sea level, but what's bringing trouble to the coastline is the extreme sea level. So that's when a short period of time, maybe 1 or 2 days, the sea level gets heightened by storm or atmospheric weather. And these events will be a lot more common in the future. And this is a bit complicated picture that tries to explain the historical centennial extreme event, HCEs. So that's the statistical 100-year storm level. So that's a level that happens statistically every 100 years. And that means for Sweden about 1.5 meters or so. So if the sea level rises 1.5 meters for a day, that's a kind of type of event. And these events will get a lot more common in the future, if you raise the mean sea level. That's important to think about, because it's easier to try to adapt to a slowly rising mean level than to these extreme events, and they are usually very, very costly for society also. And here I've highlighted this finding from the SROC also, that these centennial events, at least annually by 2050, regardless of what emission scenario. So if I would pick out just one finding from the SROC that's the most grave, it would for sure be this one. So it means that the 100-year storms will happen every year at 2050 for low-lying areas, and including mega cities in Asia, Jakarta, Bangkok, Calcutta, and those places. So that will be a very large increase in frequency. And also since this time, there was a paper in 2019 that said that we have probably underestimated these areas that are prone to flooding due to this lack of satellite data in some areas before. And as with many aspects of the climate change, it's a very unjust problem, and this is also the case with sea level rise. The poor people will be hit the worst. And here's a picture from about the situation in the South Pacific. So the small island nation of Kiribati, they have already bought land on Fiji, which is higher lying, because they know that their whole country will be erased in the future. And the big problem is here that these small atoll islands, they will be overrun by salt water. And that's going to happen quite soon. This picture below here is from a study that also looked at the wave action. What are the waves doing to these small islands? And they make that the overwashed waves come in and affect the groundwater here. Most studies before only looked at the slow rise of the sea level. So it would actually be possible to have houses and stuff, but you have to move from these islands because there's no fresh water when this happens on a regular basis. And also here's another interesting study from just this December, and it argues that the IPCC projections for sea level rise are probably too low for the high emission scenarios, and they have actually been for quite some time way too conservative. And they put out the arguments very nicely in this paper. And the graph shows here that the melting of the ice sheet is actually following the high emission scenarios from the former IPCC assessment. So I don't know if you're aware of this debate that the high emission RSP 8.5 scenario, there was a debate that this was regarded as an unrealistic scenario and this could never happen. But mostly this referred to atmospheric heating, but for sea level rise, you can definitely get these kind of levels from this scenario, which this graph shows. And the problem here is that there's lots of uncertainty about the stability of the ice sheet, and the models cannot really get all these small details. You have to have a really, really high resolution to run the ice sheet model coupled with the global models. And they're still lacking information about the bedrock and the ice dynamics on site here. And they also show that we have historically had very, very fast melting. It has happened before for relatively low forcing. Yeah. Yeah, then also a quick peek into Sweden here. And these are not Swedish albatross, they're from the Southern Ocean, but they can maybe show that what's happening in Antarctica will also be very important for Sweden in the future. And here's an example what happens sometimes. This is from the storm Gorm, when the sea level was temporarily raised by 2.5 meters in southern Sweden. Here is Ängelholm. And when we talk about sea level rise in Sweden, it's a very important factor is the post-glacial land rise, which differs along places along the Swedish coast. So Skåne has almost no land rise. Göteborg 3 millimeters per year, Stockholm 6. And the largest land rise is here along Höga Kusten, so that's almost 1 centimeter per year. And this will continue for a couple of thousands of years with the same speed. So this will always influence sea level rise in Sweden. And here is a study that shows also the difference in different parts in Sweden. So these are projections to 2100 of the mean sea level rise, basically. So this left side here is RCP 2.6, which is the low emission scenario, and the right side is the high emission scenario. And there are also southern Baltic, so this is basically Skåne, northern Baltic, which is Norrland. And here you can see for the low emission scenario, there will be some sea level rise in Skåne, but in the north, the land rise will keep outrunning the sea level rise. So you will feel as the land is also rising still in the northern part. And to the right side, the high emission scenario in Skåne, we could get a bit over half a meter or so of mean sea level rise. And this almost equals out for the southern parts of the Botnian Bay here. But there's still some land rise on this. So this will not be a problem on the coast of Norrland for a couple of 100 years, but we already have huge problems in Skåne, and there will be a lot worse in the future. This is one example what is happening now. Now there's a wall 20 kilometers long that built around Falsterbo here to protect from the ocean. And there's also the problem with the soft coast in Skåne, so there's lots of erosion. Okay, that was it. I hope I didn't continue for too long.